Hi, this is Kiffer with this week's lecture on multivariable modeling, where we're going to talk about multiple, linear, and logistic regression, and give you kind of a working understanding of what regression is and its relationship to correlation, and also what kind of the implications are of multivariable modeling and what assumptions do we make when we create a multivariable model. On slide 2, you can see that we kind of introduce two concepts that are very closely related, but are, I think, considered quite distinct: the correlation and regression. And so correlation describes the nature and strength of a linear association between two variables. So say if you were interested in looking at something like the relationship between height or weight, you would plot weight and height together. It doesn't really matter which is causing the other, right? There's no sense of causation. It's just simply correlation. We have all, of course, heard that saying before, that correlation does not necessarily mean causation. And so with correlation, oftentimes, if you are interested in the relationship between some sort of causal factor, so say you were looking at like the relationship between IQ and math test scores, you might plot IQ as the independent predictor variable as x, and then the y variable would be your dependent outcome variable, and that might be your math scores. And so if you plot those, you could imagine there would be some sort of relationship. And so when correlation is involved, you're simply trying to describe the nature of that relationship. However, when you start doing a regression, you're really interested in seeing what is the mathematical model that describes that relationship. And this you might be familiar with from math class, where you had y equals mx plus b. Remember, y is the size of the outcome variable, is equal to mx, m being the slope, x being the level of x that you're interested in, and b being the intercept where it crosses the axis. And so this is simply, for the sake of statistical methods, we just simply reorder this. We say that y equals beta 0, which is the intercept, plus beta 1 x. And that's the effect is beta 1. The effect of for each level x is by a linear relationship, just b1. And so you can see that these two lines here on slide 2 kind of are different equations to attempting to describe this data. But as you can imagine, one of these lines is probably better fitting, and so we often talk about what we call theoretically the best fit line. And on slide 3, you can see that we determine the best fit line by taking into consideration the residuals, or in other words, the difference between the predicted y value and the observed y value for any given level of x. And so it's ultimately just the observed y minus the predicted y, or the length of the black lines as are depicted on slide 3. And so you can calculate for each line hypothetically what those distances might be, and you'd be interested in minimizing that relationship if possible, to shrink down the most. However, on slide 4, you can actually see that there's a bit of a problem with that, because if you add up all the positive residuals for a good fitting line and all the negative residuals for a good fitting line, you actually get into territory where the positives kind of wipe out the negatives, plus 18 here and minus 18 for the ones below the line. And so this is because, of course, if you have a line that's perfectly in the middle and perfectly describing the data, then it's going to add up to 0. Therefore, instead of adding up all the residuals, is what we do is we sum the squared of the individuals. And you can see this on slide 5, where the residuals for a good fitting line add up to 0. When we square them, this is no longer true, because whenever you square a negative number, you might recall it becomes positive. And so instead of having negatives and positives, those kind of don't wipe each other out. They just end up with two positives. And so your goal is not necessarily to minimize the residuals, but to minimize the squared value of the residuals. And this is also referred to as your regression error, or your unexplained variation. And again, it's simply calculated by summing up all of the differences, so all of the residuals squared, and using those calculations to achieve kind of a minimum least square regression. On slide 6, we kind of show that this can be thought of as kind of a contrast to what we would call the total error or the total variation. And with total error, instead of like putting in the line where you think the data fit, you would just calculate the mean and then calculate all the deviations from the mean, and that's the total error, right? Because you can imagine in the sampling distributions that we've been talking about throughout this course, when you collect a sample, you assume that you're really calculating everything based on the sample mean, because that's your measure of centrality. And so any deviations from that mean are the total kind of deviations in your data. And so on slide 7, you can kind of get the sense that these two factors are important, both the regression error and the total error. And indeed, if you take 1 minus the regression error divided by the total error, you get a value that we call the r squared. And this is an important measure because it tells you the proportion of variation in the dependent variable, or also known as the y variable, that's predicted by the x variable. And this allows you to get a sense of how good of a model you have. And so you can see on that kind of that top first graph, an r square of 0.33 doesn't describe the data especially well. It's okay. It explains, like I said, about 33% of the variation in y could be explained by that line, by the x relationship, and is modeled in that line. But if the data were much less spread out and much closer fitting to that line, you can see that the r square is 95%, and that most of the variation is just very small within very close to that line. And so it tells you just how good of a model you have when you have a single variable predicting an outcome variable. And so this is an important thing to be aware of. On slide 8, we introduce the linear regression coefficient and how to interpret it, because when you conduct regression, you get these beta values, right? And so if you remember on, I think, slide 2 or 3, we introduced the y equals mx plus b being reformatted to y equals beta 0 plus beta 1x. Well, how do you interpret that beta 1x? Well, for a continuous predictor, the beta coefficient, or the regression coefficient, is the per unit increase in y for each unit increase in x. And so as you move x up, it's multiplied by that factor, and you know what kind of level it is at any given level. You can predict that. And so for a binary predictor, however, this relationship changes so much, because a binary predictor, you can't just move up indefinitely. So for a binary variable, we create what we call a dummy variable. And so take gender, for instance, we would have males equals 0, females equals 1. Now you could switch that over depending on which one you want it to be the reference group. And the reference group would be the one indicated by 0. And so you can imagine in a regression equation that y equals beta 0, which is your intercept. That is just determined on its own. That's kind of not relevant to you. But beta 1, if it's male, it would be 0, and if it's female, it would be 1. And then if you multiply that by the level, right, then you, the male or female, then beta 1 will equal to 0 if it's male, but then it will equal whatever beta 1 is if it's female. And so a kind of a simpler way to say that is that you create a dummy variable for binary predictors, and simply the beta coefficient is the change from male to female, or the change from the referent level to the level of interest. And then there are also categorical predictors, which again here we created a dummy variable. So if we're interested in something like ethnicity, we'd create one for white, one for black, one for Asian, one for indigenous, or whatever ultimately, categories you're interested in. And then it would simply be the coefficient that's added based on whichever of those values is indicated. Because we wouldn't want to assign it, 1 white, 2 black, 3 Asian, 4 indigenous, because right, it doesn't make sense to multiply it by, those are what we call kind of categorical and not ordinal variables or interval variables, where the relationship kind of makes sense to consider in terms of a linear. Now you might have something like strongly agree to strongly disagree on a scale, where maybe you would treat those as categories, but maybe you would just treat them as a continuous predictor or something similar. However, it's worth noting that with Likert scales, oftentimes those tend to have a logarithmic relationship. Empirical research has shown. And so that's slide 8. On slide 9, we kind of introduce this concept of multiple regression. And this is a little bit more difficult to understand than linear regression. But multiple regression has this concept of a response plane. And instead of just simply having an x variable and a y variable, you'd have multiple independent variables signified by x representing a dependent variable represented by y. And you can see that in this equation, the value remains basically unchanged for the intercept. It would just be whatever your intercept is. You don't need to worry so much about that. But then B1 would have its own relationship to y, and B2 would have its own relationship to y. And that those would kind of fit on what we would consider a linear plane. And so this is just another conceptualization, and you can imagine that we would still calculate the least squares to minimize the observed data from the predicted data that's predicted by your response plane. And you can imagine that as you add variables, these become increasingly complex and difficult to represent. And so, of course, in multiple regression, you're not calculating these by hand or anything. These require advanced statistical software to really describe their effects. Now, starting on slide 10, there are some important considerations when conducting multivariable regression, and really all regression in general. The first is that your data is normally distributed, and so this basically fits that classical normal distribution which you've learned about, and that your data isn't something like uniform or bimodal or right skewed. And you can see kind of examples of how those lines would differ. You know, something like bimodal is interesting because if you calculate the mean of bimodal, it looks like it has a mean. If you calculate the median, it looks like it has the same median. And so you might assume just by calculating those two variables that you have a normally distributed character. When, you know, with the right skewed, you would get the sense that the median and mean don't line up because remember the mean is attracted towards the coefficient. And so it's important to actually be able to chart your data out to get a sense of what is the distribution. So we use histograms for that. And understand if it's normal, then you can kind of proceed with these standard distribution-based methods like regression. And if it's not normal, you might choose what we call a non-parametric method, which we're going to discuss in next week's lecture, and get a better sense. The next important thing on slide 11 is that the relationship between your variables is linear. And you can imagine, for instance, that the relationship for like a binary variable can only take on the value 0 or 1. And so we use actually what we call a logistic distribution for that. There's also exponential models and logarithmic models and inverted U models, where these are ultimately just more complex lines. But for linear regression, we make the assumption that the relationship is kind of constant, that it's just kind of one line accurately describes the data, and that it's not some weird relationship like a logarithmic or inverted U. Now, we actually know that, like, for instance, inverted U, there are things that are kind of on an inverted U relationship. For instance, I've read some research on class sizes for like classes for elementary school kids, that the class size is kind of got this inverted U relationship, that students tend to do better in small class sizes, but there reaches a point where they don't do so well, and then if it's a larger size class, then they kind of start to improve again. And so these sort of things are just kind of the natural distributions of the relationship between two variables, and there's not much you can do about that. But suffice it to say here that if we're conducting a linear regression or a logistic regression, then the relationship should be somewhat based on those distributions which you'll use. And you can use transformations and functions to try to fit things to these various You can try to force a logarithmic relationship or an exponential one into a linear relationship by using some sort of transformation. But ultimately, those just make interpretation more complex, and so you have to be somewhat careful when you do that. On slide 12, we introduce the next kind of basic principle of logistic regression, and that's that you don't have what's called heteroscedasticity. And so that just means that your residuals are kind of constant, that like they don't increase with age. See how the residuals are much different in the second half of that we'd call this graph on slide 12 heteroscedastic, because the errors or the error terms or what we call residuals has a non-constant relationship that maybe you can imagine with age. Maybe when people are younger, the relationship has some degree of accuracy. It's r squared would be pretty good, but then as you age, the relationship becomes less clear. And so maybe that's because there becomes a second factor that's involved, that's kind of clouding the data. It could be really due to anything. So stratifying might fix that, but it might not. And so you basically got to plot your residuals is what we do for this, and we basically get a sense of, well, are the residuals fairly constant? And while they needn't be exactly constant, if you see big spreads in the data, then that's when you'd be concerned if those are changing. And then on slide 13, kind of the next consideration is your observations have to be independent. So this runs you into trouble when you've recruited from things like schools, or when you've recruited from maybe families or something like that, where the relationship between variables might be correlated within individuals. And so linear regression and most regression techniques actually assume an independence of observations. And the best way to achieve that is a random sampling, or basically some way to kind of make sure that your observations aren't dependent on one another. And then slide 14, another important issue is called multi-collinearity. And this is ultimately that when you have a number of independent predictor variables, that they don't kind of overlap too much. You can imagine for certain things like race and income and health, those things all might be kind of too strongly correlated with each other. And so when you run a regression, those factors are too hard to kind of parse out from one another, and you run into an issue of what's called multi-collinearity. And so you do tolerate some multi-collinearity. Obviously, they can overlap some degree, but it's not good to have a model where lots of your variables are what we would describe as collinear. And so we generally avoid that by selecting our models carefully. There's a number of variable selection techniques, forward selection, backward selection, that these are both basically ways to identify the variables that are most appropriately included in your model, and to not include the variables that basically can be represented by just one. And then on slide 15, remember this is just an adaptation of linear regression called logistic regression, where we take the logistic, we basically put a logistic root function on the probability, and then basically we interpret the beta coefficients a little bit differently, which we'll show in the next slide. But for logistic regression, just to refresh, the outcome is dichotomous. 1 is the event, 0 is the non-event, and p is the probability of the event. The outcome is modeled in what we call log odds, and so the model parameters we use are estimated using a maximum likelihood technique, and this helps us just to deal with the relationship between logs and probabilities. And so the beta 1 value there would be equivalent to the log odds ratio, and so you can exponentiate a beta to get the odds ratio. Or sorry, the beta 1 is just the log odds, and then if you exponentiate, you get the odds ratio from a logistic regression model. And so you can see our interpretation on slide 16 of the regression coefficient is a little bit different. For a dichotomous predictor, beta 1 is the log odds comparing groups to the referent level. With a continuous predictor, it's a log odds per unit change. And so remember, as we interpret, say we're looking at something like age and heart attack. Heart attack being a binary variable, yes or no, right? As you age, the odds of a heart attack are going to increase per year of increasing age, or maybe you'll say per 10 years, whatever the unit you decide to include in your model. And so then you can exponentiate those and get an easily interpretable odds ratio, which you should be familiar with at this point. And so that's multiple logistic and linear regression for you. In slides 17, 18, and 19, we have some practice questions which can kind of help guide you on what to study, what you might be interested in evaluating on a quiz, for example. And so if you have any questions, I look forward to addressing them on the discussion boards. And until then, have a good week.